Picture this for a second. You're strapped into a small spacecraft, floating miles beyond Earth, and outside your window there is nothing but endless black. No sound, no wind, no life, just silence stretching in every direction. Now imagine you're not there for a few hours or days, but for years, maybe even the rest of your life. No rescue mission is coming. No supply drops. No second chances if something fails. That is the reality of deep space, and it is far more unforgiving than most people are willing to admit. We love to talk about becoming a spacefaring civilization, about building colonies on distant planets, about pushing humanity beyond Earth. But between that dream and reality is a brutal truth that starts with a simple question. How do you actually stay alive out there when everything your body depends on no longer exists naturally? On Earth, survival feels effortless because everything we need is already built into the environment around us. Air is everywhere. Water cycles endlessly. Food grows from the ground. The planet itself is a perfectly balanced life support system that has been fine-tuned over billions of years. But the moment you leave Earth, that entire system disappears instantly. Every breath you take must be manufactured. Every drop of water must be recycled. Every calorie you consume must be carefully stored or artificially produced. Nothing comes for free anymore. And this is where the first major problem begins to reveal itself. Even with our most advanced technology today, we are nowhere near fully self-sustaining in space. Take the International Space Station as an example. It represents the peak of human engineering in orbit, and even there, survival is a constant balancing act. The station can recycle roughly 90% of its water, which sounds impressive at first, until you realize what that remaining 10% means over time. On a mission lasting months, it is manageable. On a mission lasting years, it becomes a slow countdown to failure. That missing fraction accumulates day after day, week after week, and eventually, you run out. There is no hidden reservoir waiting in space. There is no way to gather fresh water from the vacuum. Once your supply is gone, that is the end of the mission. But water is only part of the equation. Oxygen must be continuously generated, carbon dioxide must be removed, and all of this depends on highly complex machines that cannot fail. These systems are not simple devices you can fix with basic tools. They require maintenance, replacement parts, and most importantly, energy. A massive, constant supply of energy. On the space station, that energy comes from large solar panels that absorb sunlight as the station orbits Earth. But as you travel farther away, that reliable energy source begins to fade. By the time you reach the outer planets, sunlight is dramatically weaker. In the depths of interstellar space, it is essentially non-existent. You might think nuclear power could solve that problem, and to some extent it can, but even nuclear systems rely on finite fuel. Once that fuel is depleted, everything shuts down. Air production stops. Water recycling fails. Temperature control disappears. And in space, temperature is not just uncomfortable, it is lethal. Without controlled conditions, a spacecraft can become either a freezing tomb or an overheated chamber within a short period of time. Every system is connected, and when one fails, the others begin to collapse in sequence. So why not just bring more supplies to begin with? It sounds logical, but it introduces another major obstacle, and that is mass. Every kilogram you send into space requires an enormous amount of fuel to launch and move. The heavier your spacecraft becomes, the more fuel you need, and that additional fuel itself adds more weight. It creates a cycle that quickly becomes impractical. You cannot simply pack enough resources for decades-long travel without facing exponential increases in cost and complexity. Even if we somehow overcame these resource limitations, we would still face an even harsher barrier that cannot be engineered away so easily, and that is physics itself. Space is unimaginably vast. The closest star system to us is over 4 light-years away. That distance might sound abstract, but when you break it down using our current technology, it becomes almost impossible to comprehend. Our fastest spacecraft would take thousands of years to reach it. Not decades, not centuries, but thousands of years. That means multiple human lifetimes just to arrive at the nearest destination. And then there is another misconception that people often have about space. Many imagine it as completely empty, a perfect void where nothing exists. In reality, space is filled with countless particles and objects moving at extreme speeds. Tiny fragments of dust, micrometeoroids, and debris travel fast enough to cause catastrophic damage upon impact. A particle no larger than a grain of sand can strike a spacecraft with the force of an explosion due to its velocity. It is not just a risk, it is an inevitability over long distances. Even in low Earth orbit, where we can track objects and predict collisions, spacecraft still face constant danger. Protective shielding can reduce the risk, but it cannot eliminate it. In deep space, where tracking is nearly impossible, every second becomes a gamble. One direct hit to a critical system could end everything instantly. A breach in the hull means loss of air. Damage to power systems leads to freezing conditions. A compromised recycling unit means dehydration. There are no backup crews, no emergency evacuations, no quick fixes. And even if nothing dramatic happens, even if there are no collisions or catastrophic failures, the slow breakdown of systems is unavoidable. Machines wear down over time. Components degrade. On Earth, when something breaks, you call for help, order parts, or replace the entire system. In deep space, you only have what you brought with you. If a critical component fails and you do not have a replacement, that is where the journey ends. Small problems can quickly cascade into larger ones, creating a chain reaction that becomes impossible to control. This is the harsh reality behind the dream of deep space exploration. It is not just about building a bigger rocket or a faster engine. It is about solving a series of interconnected problems where failure in one area can lead to total system collapse. And right now, even with all our advancements, we are still incredibly dependent on Earth for survival. The idea that we can simply leave and thrive in deep space is not just optimistic, it is dangerously underestimated. And this is only the beginning of the problem, because even if we somehow build a spacecraft that can sustain life perfectly for years or decades, there is something even more fragile than our technology. Something we cannot replace or repair so easily. Our own bodies. Now imagine you've somehow solved every engineering problem. Every system is running perfectly. Your spacecraft is stable, your supplies are managed, and nothing has broken. You might think at that point the hardest part is over, but this is where the real challenge begins. Because the greatest weakness in deep space is not the ship, it is you. The human body was never designed to exist beyond Earth, and the moment you leave this planet, you begin to change in ways that are slow, silent, and often irreversible. One of the biggest threats comes from something you cannot see or feel immediately, and that is radiation. Here on Earth, we are protected by a magnetic field and a thick atmosphere that shields us from most harmful cosmic particles. In deep space, that protection disappears completely, leaving you exposed every second to high-energy radiation that passes straight through your body. This is not the kind of radiation you get from a medical scan or a brief exposure to sunlight. These are particles particles traveling at nearly the speed of light, capable of penetrating spacecraft walls and damaging your DNA at a cellular level. Over time, this damage builds up, increasing the likelihood of cancer and other serious conditions. On Earth, the average person is exposed to a small amount of radiation each year, barely noticeable in its effects. On a space station orbiting our planet, that exposure increases dramatically. But once you leave Earth's magnetic protection, the levels climb even higher, reaching a point where long-term survival becomes extremely questionable. The most troubling part is that this damage does not simply go away. It accumulates. Your body tries to repair itself, but it cannot keep up indefinitely. Each exposure adds to the previous one, creating a gradual breakdown at the genetic level. Even if you were to return home after years in space, the effects would remain inside you, continuing to influence your health long after the journey ends. It is like carrying an invisible clock that has already been set in motion, with no way to reset it. At the same time, another process begins to take hold, one that directly affects your strength and physical structure. In the absence of gravity, your muscles no longer need to support your body weight, and your bones no longer bear the load they evolved to handle. The body responds quickly, reducing what it no longer considers necessary. Muscles begin to shrink, and bones lose density month after month. Even with strict exercise routines designed to slow this process, the decline continues. Over extended periods, the loss becomes severe enough to fundamentally change your physical capabilities. Imagine spending years in this environment and then attempting to stand under normal gravity again. Your legs, once strong and stable, may no longer be able to support your weight. Your bones, weakened over time, could fracture under pressure that once felt effortless. The very act of walking could become dangerous. This is not a temporary inconvenience, but a transformation that could define the rest of your life. Your body adapts to space in a way that makes returning to Earth increasingly difficult. Your cardiovascular system is also affected in ways that are less visible but equally serious. Without gravity pulling blood downward, fluids shift toward your upper body, creating a constant pressure in your head. Your face may appear swollen, your sinuses feel blocked, and your vision can begin to change. The structure of your eyes can alter, affecting how you see the world. Meanwhile, your heart, no longer working against gravity, becomes less efficient over time. It adapts to an easier environment, but that adaptation becomes a disadvantage the moment you reintroduce gravity. The immune system, which protects you from illness, does not function the same way in space either. Its effectiveness decreases, leaving you more vulnerable to infections that would normally be minor on Earth. At the same time, viruses that have remained inactive in your body for years can suddenly reactivate. Illnesses you thought were long gone can return without warning. Healing slows down, meaning even small injuries